Good afternoon, teacher. My name is Dong Kun. I'm an information and computer science student. Here I will give you a presentation about final year project, which is enhancing the security of numeric compression secure symbol pairing protocol in Bluetooth Standard 5. This presentation will be divided into these 5 parts. Firstly, I will introduce the background of my project. I believe many persons are using Bluetooth technology for short-range wireless communication, such as wireless headset, TV remote control, and the door lock system. The security of Bluetooth is the principal factor that can influence the user's choice of the device. But I found Bluetooth technology has some safety problem. Let's analyze it. Bluetooth technology needs to store a long-term key in device, but this key can be learned by standard channel attack, such as timing attack or power consumption attack, because the security of Bluetooth protocol assumes computational method is the only attack technique. So it's a fatal problem that can leak the user's information. According to this question, I also searched some literatures. First is Bluetooth SIP protocol. This protocol has been used after Bluetooth version 2.1. It can prevent computational attack, but until the current version 5.2, the Bluetooth technique just improved the faster transmission speed and the longer propagation distance. There is no security improvement against the single channel attack. And then I also found some methods that can prevent single channel attack for the long-term key, but they can only be used in other protocols such as ECT model and digital signature. According to my research, there are no methods that can be applied in Bluetooth SIP protocol. So, the aim of this project is to improve the security of Bluetooth SIP protocol against the single channel attack. 2 leakage-resilient Bluetooth protocols will be introduced in the third part. Both of them use different methods that are exponent splitting and multiple curtail mask. Before that, let's talk about some preliminary knowledge. First is elliptic curve diffie-Hellman. If elliptic curve meets this function, it will have some operations that can be used in cryptography. I choose one of the operations called scalar multiplications as an example. Firstly, if I choose a constant number t times a point p in elliptic curve, it is easy to find this point r in elliptic curve. But if I get this point p and this point r, it is very difficult to calculate this constant number t. So, in symmetric cryptography, we can set this constant t as a private key, and this point r as a public key. Let's see the detail of that. In elliptic curve diffie-Hellman key exchange, I assume the device A as the initiator and the device B as a responder. Firstly, device A should generate a private key A and calculate the public key A equals private key A times J. J is the base point in elliptic curve that everyone can know. And the device B does the similar operations to generate a private key B and a public key B. And then, both of them send the public key each other. Finally, they can get the same shared key, which is private key A times private key B times J. In Bluetooth technology, the private key A and the private key B are the long-term keys that will not be changed in device. So, this is the first stage of the Bluetooth SIP protocol called public key exchange. My designed protocols are based on it. The rest stage are not changed in my protocols, so I only introduce them briefly. The second step is authentication stage 1. It can prevent man-in-the-middle attack by double hash functions. Authentication stage 2 can verify if authentication stage 1 completes successfully. Next, the link key will be generated and encrypted. It can be used in next other Bluetooth protocols. So, this is all my preliminary knowledge. In part 3, I'm going to explain my improved Bluetooth protocols the new protocols can refresh the long-term key values against the single channel attack. Let's see the detail. In Protocol 1, it uses its exponent splitting method. Firstly, device A generates private key A and random number RE1 and calculates RE2 equals private key A minus RE1 and drop its private key. So, device A only stores RE1 and RE2, but RE1 plus RE2 is equals to private key A. And next, device A calculates the public key A equals RE1 plus RE2 times J and send it to B. Device B does the same operations to generate the RB1 and RB2 and send its public key to A. Next, let's prove how they can get the same shared key. I use device A as an example. Firstly, the device A calculates the temporary value K1 equals RE1 times public KB, and then it calculates the temporary value Ka2 equals RE2 times public KB. So, the same shared key is equals to K1 plus K2. But if we simplify it, it's also equals to private Ka times private Kb times J. And the device B can also get the same shared value. So far, both device A and B get the same shared key, but there is an important step is to refresh a long-term key. After key exchange, device A should generate a new random number RE3 and calculates the RE1 equals old value RE1 plus RE3, RE2 equals old value RE2 minus RE3. So, the new value RE1 plus the new value RE2 is also equals to private key A. And the device B can also do the similar operations to refresh the RB1 and RB2. So the new value RB1 plus the new value RB2 is also equals to private key B. Because their long-term key numbers will be changed after each connection, side channel attack can't get any information about the long-term key. Next, let's move on to my second protocol. It uses multiplicative max method. Firstly, device A generates a private key A and random number RE1 and calculates the number RE2 equals private key A over RE1 and drop its private key. So, device A only stores this number RE1 and this number RE2. But RE1 times RE2 is also equals to private key A. And then device A calculates the public key A equals RE1 times RE2 times J and send it to B. Device B does the similar operations to generate the RB1 and RB2 and send its public key to A. So, let's prove how they can get the same shared key. I also use device A as an example. Firstly, it calculates the temporary value Ka1 equals RE1 times public Kb, and the shared key is equals to RE2 times Ke1. And if we simplify it, it's also equals to private Ka times private Kb times J. And the device B can also get the same shared key. Next step is to refresh a long-term key. After key exchange, the device A should generate a new random number RE3 and calculates the RE1 equals the old value RE1 times RE3, RE2 equals the old value RE2 over RE3. So, the new value RE1 times the new value RE2 is also equals to private key A. And the device B does the same operation to refresh RB1 and RB2. So the new value RB1 times the new value RB2 is also equals to private KB. So those are my improved protocols. Both of them can prevent side channel attack by refreshing the long-term key. Next, I will evaluate my protocols by computation cost and the communication cost. In order to evaluate the computation cost, I calculated the number of scalar multiplications, denote S, and hash functions, denote H. We can find my input protocols are 2 more scalar multiplications than the standard protocol. Maybe it causes my protocols need longer wait time. Next, communication cost needs to record the number of transmitted message, denote M. We can say all of them have 8 times, so my improved protocols just use a little more computation cost to prevent side-channel attack. After we evaluate them, let's move on to how to implement them. I used 3 devices, a laptop, a router, and a Raspberry Pi. In addition, I used Python to realize my protocols. Because Python has rich libraries, I can use ECC library to achieve elliptic curve and HashLab to achieve hash function. And my completed code will be shown in my dissertation. Next, let's talk about the results of my experiment. I executed every protocol 10 times. This table shows the average computation time with 256 base elliptic curve. We can find first improved protocol it has a longer runtime than the second one, because the first protocol has an extra addition operation. I also try to use different elliptic curve to realize my protocols, and the results are similar with before. So my improved protocols just increase a little runtime against the side-channel attack. To summarize, I have designed 2 improved Bluetooth protocols against the side-channel attack and realized them successfully. In the future, I will design a protocol that can use less time against the side-channel attack. This is reference I used in my presentation. So this about is my final year project presentation. More detail of that will be shown in my dissertation. Thank you.